Pulleys and wedges, type 3, fixed string, 2 accelerations. So in 1997 we had a diagram showing a light inextensible string, meaning that the pulleys and also the masses aren't going to be bouncing up and down. And we're told that one end is fixed at O, so this is the fixed end, and it's passing under being important here, a smooth movable pulley of mass kg. So we have a bit of an abstract question here where we're going to have an unknown letter in our question. But we still treat it exactly the same way as before. It'll just look a little bit different than normal. And the fact that they're both smooth pulleys, both C and D, that means we're going to have no friction in either case. And then we're then told that the other end of the string is attached to a particle E, which is of mass m kilograms. So in this case, we're very specifically asked to show on separate diagrams the forces acting on it. So we always do this anyway, but this time because we're being asked for it, we're being specifically marked on it. And again, we're told the system is released from rest. So we're going to start with part 1. So before I break down the diagram, I'm going to look at the overall picture so we can see what's going on overall. We won't get marks for this diagram, however, because this is not separate diagrams. So I always draw the overall picture and then break it down. So we have our weight is equal to our mass times gravity. So therefore, if E is going to be of mass m, well, we have mass times gravity, so that's going to be mg. C has a mass of km, so therefore that's going to be km times g, acting down. And we're told D is a smooth light pulley. So when they say light pulley, they're saying negligible mass for this particular question. Now it's one string, so therefore we're going to have common tension, and tension always acts away from the object. So therefore we're going to have T, and our pulley here, the string is going under it, so that's going to be taken into account because this can move. So therefore we have to put tension here as well. Now what's going to happen? Well, what we're going to look at is the fact that the string is going under C, means that we have, if it moves up, the string is going to lengthen, and therefore it's going to become free, and therefore the particle E would move down by twice the length that C moves up. So of course the relationship for these questions is then that there are two different accelerations. So we say the one that is accelerating, I'm going to say mg is going to accelerate down, and therefore this one would accelerate up. So if we're going to say A and B. Now what happens if I get those two the wrong way around? Well, if I had those two the wrong way around, what would happen is I'd end up with a negative value, and therefore that doesn't matter as long as you state that actually the direction was the other way around. Okay, and therefore if I knew what the masses are, we would actually half the one with the string going underneath it, and therefore we would be able to see which side was heavier. Okay, so the relationship then is that A will accelerate twice as fast as B because of the string freeing up on both sides of C. So that's going to be key to solving this question. Okay, so now we have the big picture. We're going to break it down into our part 1, our separate diagrams on each particle. So I'm going to start with E. So E is the first diagram. So we have tension acting up, and we then have the weight acting down, and I'm saying it's accelerating down. So we only have vertical motion here, so therefore our net force will equal ma. So because it's accelerating down, our leading force will be the weight, and the opposing force will be the tension, and the net force then will equal mass times acceleration. So we have mg minus t is equal to ma, and therefore t will equal mg minus ma. So I'm going to call that equation 1. So we're then going to do the separate diagram for C, and C is our pulley, which then has the forces acting up on either side, which is our tension on either side. And we then have the weight acting down, which is kmg. And again, our net force is going to be the leading force here, because it's going up, will be the tension. So I have two tensions going up, and then I have weight going down equals mass times acceleration. But of course the weight is kmg, the mass in this case is km, and the acceleration is b in this case. So therefore we end up with 2t is equal to kmg plus kmb. So now we have a second equation. And what I need to do next then is say, well, I have t in one and t in the other, so I'm going to multiply the first equation by 2. But I'm also going to be looking for the upward acceleration of c. In other words, I'm looking for the acceleration b. So I'm going to sub in a is equal to 2b into 2, and I'm going to, into 1, sorry, and I'm also going to double 1. So my part 1 is done because I have my two diagrams drawn, and next to them I've written out my two equations, which is for part 2. Okay, so by doubling the first one, I will get 2t, which means I'm going to equate 1 and 2 because they'll both be equal to 2t. So by doubling the first one, I end up with 2mg minus 2ma. So that would become 2mg minus 2ma. And that's 2t. And that will equal kmg plus kmb. But I'm going to say, but a is equal to 2b. Therefore, I have 2mg minus 2m times a is 2b. And that's equal to kmg plus kmb. So I now need to try and isolate b on its own. So that's 4mb is equal to kmg plus kmb. So I'm going to bring all of the b's to one side. So I have kmb. So kmb plus 4mb is equal to 2mg minus kmg. And I can see that mass is going to divide all the way across there. So m is going to go into each of those. If I take out b as being common here, I get k plus 4. And then if I take out g as being common there, I have 2 minus k times g. So dividing across by k plus 4, I'm left with 2 minus k over k plus 4 times g for b. And that's what they wanted us to show. They wanted us to show that c's acceleration was 2 minus k times g over k plus 4. So done. Okay, so then what does it want? Well, it wants me to find that if k is equal to 0.5, now we want to find the tension in the string. So of course the tension in the string is T is equal to mg minus ma, and I know that A is equal to 2b, and I know that B is equal to 2 minus k over k plus 4 times g. So therefore I can say, well, A is equal to 2b, so A is going to equal 2 times 2 minus k, so that's going to be 4 minus 2k times g all over k plus 4. So in other words, I just double b to get a. And therefore I can sub a into the first equation. So I'm going to sub K equals 0.5 and A into equation 1 to work out what the tension is. So my tension, if I go back, is mg minus ma. So that's mg minus ma. But A we've just worked out to be 4 minus 2k. So 4 minus 2 times k is 0.5 times g. And that's all over k plus 4. So that's 0.5 plus 4. So by simplifying that, we get mg minus, so 4 minus 1 times g is 3g, so that's going to be minus 3mg on the top, and then on the bottom it's 4.5. So therefore we have 3 divided by 4.5 is basically 2 over 3. So that's mg minus 2g over 3. And then lowest common denominator there is 3, so that leaves me with g. That should be an m there as well, sorry. Write that. So that's 2mg over 3. So lowest common denominator is 3, which leaves me with 3mg minus 2mg, which is just mg over 3 is our tension. Okay, so where were our marks going for this? So it was 10, 25 marks total. So we had 5 for the diagrams. And then we had 5 for both equations, so equation 1 and equation 2. And then we had 5 for working out our acceleration of c. And then we had 5 for getting our tension out and 5 for subbing in. Okay.